Hey, so in the past 3 lessons, we've been talking about resonance, and I've gone through it pretty thoroughly, except there's one thing I didn't mention, and that is resonance is a huge indicator of stability. So, resonance indicates stability. Oh, no, okay. And so I'll start off with an example. Um, so let's take this structure here, and this is ethanol. Now, if we want to completely remove this hydrogen shell, so this proton off of ethanol, well, it has a pKa of around 17, so it has a pKa of about 17. And what that means is that it takes a pH of 20 to completely deprotonate ethanol. And going back to acid and bases, we know that the higher the pH, the more basic a solution is. So if we need a basic solution of pH 20 to completely deprotonate ethanol, we're talking really basic stuff, right? So it takes a lot of strength to take off this proton. Now we'll look at another structure. So this is acetic acid. And if we want to take off this proton, well, it takes a pH of about 8. And that is because acetic acid has a pKa of about 4.8. So it only takes a pH of about 8, so we're talking about water here, to completely deprotonate acetic acid and to give us this structure. Okay, and you can see that we have similarities between these two structures. We have this like carbon backbone plus this oxygen. This is the same throughout the whole thing. The only big difference is this double bonded oxygen. And we haven't really talked about acid-base chemistry, but these are, the pH scale is logarithmic. So if we're talking a difference of 12 between these two solutions to deprotonate these structures, we're talking about a difference of a trillion. So basically, acetic acid is a trillion times more acidic than ethanol. Okay? And so why the big discrepancy? And we'll look at the conjugate base to find out the answer. So if we remember, conjugate bases are just the form of a molecule after it loses its proton. So let's just use this. So if we have an acid and we lose a proton, so an H plus ion, then we get its conjugate base. So acid conjugate base. Okay, so what is the conjugate base of ethanol? Well, we already drew it. It was this guy. And the conjugate base of acetic acid is this guy. And again, we haven't really talked about acidity, but I will tell you a big part of acidity lies in the stability of the conjugate base. And this makes sense because if something is really stable in its base form, perhaps even more stable than it was in its acid form, it should be relatively easy for that acid form to lose its proton to enter a state of high stability, right? So if it's easy to remove that proton, then it makes it more acidic, right? So the more stable a conjugate base, the more acidic the original acid. So let's compare the stability of both of these structures. Now, both of these conjugate bases have a formal charge of -1 on these oxygens, right? But if we look a little closer, we see that these negative charges are a little bit different. So looking at the first structure, looking at this top structure, we see that there's no resonance in this molecule. So all three of these electron pairs are stuck. So we have a localized charge, right? Meaning that that charge is stuck on there, meaning that that oxygen alone has to deal with the bear of that -1 charge. And even though oxygen is highly electronegative, like we've said before, a formal charge of 0 is still a lot more favorable than a formal charge of -1. Now, if we look at this second structure, this negative formal charge on the structure below, that's a little bit different because there is resonance, and you should be able to make it out pretty easily. We can take one of these lone pairs, we can form a double bond with this oxygen as we release this double bond to the other oxygen, right? And let me draw my lone pairs. So that gives us a structure like this. Now, this doesn't completely remove the negative formal charge, it just displaces it. But this is still a lot more stable than our other conjugate base. So we have this negative formal charge distributed between both of these oxygen atoms. So we have it between this one and this one. And a spread out formal charge is a lot more stable than a localized one like we have on our top conjugate base. And also we have our negative formal charge spread between two oxygens rather than one, meaning that both of them can handle an equal part of that negative charge. And this also makes our conjugate base a lot more stable. And this is the reason why acetic acid is 1,000,000,000 times more acidic than ethanol. And this is why resonance indicates stability, because electrons are handled over a larger area and are handled between multiple atoms. So let me write that down. I think I might need, nope, let me just do it purple. So resonance indicates stability, and two reasons: because electrons are handled over a larger area, so this means any formal charges will be spread out. Okay, yes, so handled over a larger area, which means it's more spread out, and electrons are handled between multiple atoms, which alleviates some formal charges. Handled between multiple atoms. And when I say alleviate, it means it just releases the load between atoms. I mean, the formal charge is still present. It doesn't go away, but it's handled by more atoms, which is better. And so, yeah, I think that wraps up resonance. I will probably go through some practice problems too, because resonance never goes away. Yeah, so resonance is always key. It'll be key in Orgo 1, Orgo 2, so always keep resonance in mind. Thank you. Yeah, hope this helped.